So chemical shift balance. So generally, you know that the chemical shift. So what is the chemical shift? Chemical shift is so the chemical is so that's what the chemical shift for the chemical shift is 0 to 40. So in the chemical shift range is 0 to 240. Yeah, it is what the job shift is there when you compare with the H1 NMR, because the H1 NMR range is 0 to 20 only ppm. So when where the scale is large here and where the scale is short here, so where the signals appeared in the H1 NMR is very clumsy here, very near. Okay, so very yeah, what is closer. So very complex spectra is obtained in the H1 NMR, but in the C13, so where the very large here, the 0 to you can very distance between the signal absorption distance between the signal is large here. Okay. And in the H1 NMR spectra, in the C13 also, where you can use a TMS as a solvent here. And so this solvent chemical shift value is going to absorb in the C13 spectra. So we'll have some idea about this solvents. So here the CDCl2, this is solvent, this particular multiplicity, okay, the heteronuclear multiplicity is what quintet, and where you get the absorption CDCl2 at 53.1 delta chemical shift value, and CDCl3 deuterated, and the signal plate, right? So, and you remember that in the C13 spectra, generally the multiplicity is in the line. So, uh, split uh, okay, so not like this. So you observe this kind of splitting the multiplicity in the H1 NMR. Okay, but this kind of splitting in the C13, right? Alcohol, deuterated methyl alcohol with multiplicity is septate, where the 7 lines are obtained, and the value is absorption position of this particular deuterated methyl alcohol is 0.8 here. Okay. Signal obtained is septate, and the value absorption position is 206.5 here. And again the DMSO D6, okay, DMSO. So DMSO, it is highly polar solvent generally, and it appears as the septate, and obtained at 128. Absorption position is 128. Okay, and benzene, deuterated benzene. So appearance of the signal is triplet again, and the position is 128. Like so, these values guides us, means you will get some idea about the position of here, right? So because these are not the right, the solvent peaks consider this around peak here. So if you remember these values, so then you will get idea about this one. And this, the position of the okay, the chemical shift values of various functional groups in the C13 zones. Uh, and same the carbonyl in the aldehyde group. So where the position absorption position is 190 to 200 here, and when this carbonyl is in the acetic carboxylic acids or in the ester carbonyl group, it appears at 170 to 185 here. In the arrow, it appears in the range of 125 to 150 here. Means sp2 carbon, C double bond C carbon. The range of chemical shift is 120. And in the alkenes, right, here is aromatic, and below one is it is in the alkene here, right? So aromatic So here the aromatics, okay, double bond. So it appears in the range of 125 to 150. And the normal alkene, right, double bond, this is appears in the range of 150 to 140. Yeah. And alcohol, primary alcohol, it where it appears at in the range of 50 to 65. Yeah. And the alkylates, like chlorine, appears in the range of 40 to 45. And the amines here, so the amines is absorbs in the very short delta value like 37 to 45. Yeah. And the tertiary carbon, okay, the tertiary carbon appears in the range of 25 to 35. Yeah. Means generally the alkanes appears in the very short range of the delta value. Okay, alkanes the and where this particular, okay, acetyl group here appears in the range of 20 to 30. And the secondary carbon R2CH2, it is secondary carbon here. So it is appears in the range of 16 to 25. And 15 here, right? So you will have idea about this primary, secondary, tertiary. So primary carbon appears in the range 10 to 15. And this is your secondary carbon. Okay, the secondary carbon appears in the range of 16 to 25. And a tertiary carbon appears in the range of 25 to 35 here. Okay. And these are the ranges of various function groups here. So if you see this flow chart, okay, the range of the groups where the particular group form, right, the is given, and where this particular means various groups are falls in the range of this one. Right. So if you see this carbonyl, aldehyde carbonyl is occupying the highest uh, delta value here, aldehyde carbonyl, then and ketones also near, because in the above table you can see in the ketones it is 205 to 220 here, and aldehyde is 190 to 220, 200. It is very slight difference, like 10 values differences, 10 units differences here. So you can see with the aldehyde and the carbonyl, whatever that carbonyl is in the aldehyde or the ketones, or whether it is in the carboxylic acid or in the esters. Okay, so they are having the range of up to 220. Okay, so in the range of that 192 to 200 and 220 range here. And you see that primary carbon, secondary carbons, they are having very least delta values. They falls in this uh, uh, upfield, okay, upfield or the shielded region. And where the carbonyl, they falls in shielded region or the downfield here. And if you see equivalence of, already we discussed in the previous class, okay, about the chemical shift equivalence. So here, if you take this particular alkane, okay, so the ethane here. So because it is symmetrical one, so we get only signal for this one signal for this one, because both the carbons are falls in the same chemical environment. And here also the that tertiary alcohol here, okay, tertiary alcohol where it, so generally we have because all these three, this is A, this is A, this is A here, and this is B. So you get two types of carbons in this particular tertiary alcohol, because all these three methyl groups falls in the same chemical environment here. These three are same here. Okay, so we'll get one signal for these three, and this where the tertiary carbon is. These are the primary carbon here. This is tertiary carbon. So we get the two types of carbons. So we get the two signals for this one. And in the this particular what is it? Uh, Paracresa. Uh, paraxylene, not cresol here. Paraxylene. Okay, here is a paraxylene here. So in the paraxylene, because it is symmetrical one. Okay, so generally here these two are same. This is A, and these two are same here too, and these two are okay. Here the where the okay, this is ortho. This is one type, and meta. Okay, this is second type here, and you see the okay. So it is symmetrical one, right? So we are symmetrical. So you get three types of here. Okay, so this is one for this. This is one, and this carbon is two. Here two second type here, and these orthos are one type, third type. So there are three types of protons. Sorry, carbons are present in this paraxylene, and in this para-methoxy benzoaldehyde. So we have the six types of carbons. So you can see this is one type here, right? So this is A, and these two are, this is also, this is B here, this is C, and this is D, 4. And these two orthos are one type here. So E, and these two metas are same type. Yeah. So total six types of carbons are present in this particular methoxybenzoaldehyde. Okay. So likewise here also that dimethoxy benzene, because it is symmetrical molecule here, right? So the symmetrical one here. So for this symmetrical one, so right. So where right. So we have only two chemically non-equivalent carbons here. So because you see uh, one type is these two are same here, right? Here also same, and this is second type. Right? There are types of uh, carbons. Next, the calculation of chemical shift values. So manually, right? So without recording the spectra, means without help of the instrument, see that NMR's spectral instrument. So you can manually calculate the, theoretically you can calculate the delta value, okay, chemical shift value for this. Is going to the delta value manually. So we have some base value, and we will add some additional values. Okay. So for normal hydrocarbons, okay, for normal hydrocarbons, we have the base value is minus 2.5, and the addition values are there. Yeah. Okay. Yeah. Okay, so n is the number of carbon atoms per each shift parameter here, and A is the addition shift value here, right? So and the values are additional values are given. Like if it is in alpha, it's 9.1 here. If it is in the beta, it's 9.4. If it is in the gamma, so minus 2.5, and delta plus 0.3, right? So in the examination, we will ask problem here to do the to calculate the delta value, right? So they will give the structure, okay, and they will ask to calculate the delta value, right? So you have to remember the base value and his additional values also. Okay? Or sometimes they will ask the write the calculation of chemical delta values, calculation of chemical shift values. So in that case, you have to all these table and all these formulas, everything you have to write. And if that particular tertiary carbon, okay, so tertiary carbon is attached to the primary carbon. Okay, then we have the value is minus 1 point, and the quaternary carbon is having the primary attached with primary carbon. Okay, so then means this one. So like for example here, okay, so this is tertiary carbon, and this is your primary carbon. Okay, yes. So okay, so in that case, you have to take the value of minus 1.1. Okay, and if it is quaternary carbon, this is your quaternary carbon where it is attached with the primary carbon. Okay, so for that you have to take minus 3.4. Okay, so like that we have the values for this. Now we'll see to calculate data value in point of view for the calculation of chemical values, like chain, the methyl and carbon here, right? So uh, yeah, so it is symmetrical. Okay, it's this is uh, three types four as to R is so with these two non-equivalent of R, and so 1, 2, 3, 4. So there are four non-equivalent carbons here, and we'll do the calculation of this. Uh, take this uh, here the 9.5 value is less than 5. Once it is alpha carbon, right? Is the alpha carbon is it is 9.5, and so the carbon is 9.4 and 2 minus 2.5. What this value is, it is for uh, so the carbon into the secondary one, right? So here, yes, specific carbon. This is tertiary carbon attached with secondary carbon.
Sir, screen is not visible.
Not really.
Sir, we can't see the screen.
సార్ మీ వాయిస్ కూడా బ్రేక్ అవుతుంది సార్.
So signal unstable ఉంది. So here actually here the raining. So the signals are very unstable. Okay, I'll try. So okay. Yes. So here we have two tertiary carbon attached with, right? So attached with second carbon. So for that we and 5, right? So this one. So when this tertiary carbons, okay, so secondary carbon when it is attached with the tertiary carbon, right? Then the value increment value is minus added value, not increment. So it is added value is minus 2.5. So we are taking here there are two. Okay, here is there are two secondary carbon. This is secondary carbon. This is also secondary carbon, and this secondary carbon attached to this tertiary carbon. Okay, so we are taking the here the two carbons are there, two secondary carbons attached with the tertiary. So we are taking minus 2.5. Okay, and here is one carbon minus 0.3 where the value is yes carbon is there. So we are taking the value of 0.3 and the one carbon is there, right? So the total, the calculation, when you are doing the calculation for so we got the 11.3. Okay, so we got the 11.3 calculated value. And when we, okay, when you are done this experimental, right? So when you are doing the experiment, so we got the 11.5 here. So very reliable value, means coincident value here, right? So very little difference. This is calculated value. This is experimental value, right? So this is experimental value, and this is your calculated value. So we very little slight difference, 0.2 here, 0.2 difference is there. So where this calculation is right valid here. And one more, you can see the calculation for this. So here in this, okay, so for any symmetrical compound here. So we go have the 1, 2, 3. There are three signals, right? So three non-equivalent carbons are there. So we go and we got the values for this is C1 is 14.0, C2 is 26.5, and C3 is 39. So the calculated values for this one, right? And experimental also we got say, a very slight difference, fractional difference we get. Next, the effect of substituents on alkanes. Right. So here the presence of the substituents, right? Presence of the substituents on the alkanes, how it will be impact on the delta chemical shift values. You can see, for example, here the carboxylic acid group is present at alpha position, then the value is 21. Added value is 21. And if it is in the beta terminal, right? If it is in the beta terminal, so if the branched chain. So for the non-branched compound, the values are this one. And for branched one, the values means internal will when it is a branch, and if there is branching, then values are like this here. Okay. So we'll see one example, like for example, in this 3-hydroxypentane. Okay, so so it is internal hydroxy group value here. So how it is for terminal it is 48, right? So we are taking this 3-hydroxypentane, right? So we got the 75.8 value, right? And it's also like same okay, formula is applied for this cycloalkanes, but the additional values are like means added values are is given like this here. Okay, for if it is cyclopropane ring, you have to add this 9 here, and cyclobutane 2.4 here. Okay, so like that. And alkenes also we have the values for, right? So where the for alkenes the base value taken so value taken is 123.3, right? The base value taken for this alkenes is 123.3. Then you have to means add the respective additional values. Here is a sum of examples where you can go with this. And for alkynes also, okay, and for all the, so these examples are given. Then for carbonyl compounds, right? So calculation of the delta values. So by following that, okay, by taking the base value, add the respective additional values, then you can do the calculation of that. So now we'll see the factors affecting chemical shift values. Okay, so the factors affecting chemical shift values in the also we have the factors which are affecting the delta values. In that we have various factors like electronegativity, hydrogen bonding, okay, anisotropic effect, right, and steric factors here. So these are some hybridization also the one of the major factors in this C13 values. The both cases like C13 spectra, activity delta. So here we'll see with one example. Yes. Right. So here is a methane, ethane, where this carbon is means alkane, 5.7 delta. So when the methane is attached with the electronegative, okay, electronegative oxygen atom, then you can see tremendous increase of the delta value, right? So it 5 to 59. Okay, so you can observe the drastic changes in this. Only this is this much increase is due to attachment carbon with electronegative oxygen, right? So electronegativity increases the delta value and is falls means that it falls in the downfield uh, okay downfield area, and here is some group of compounds are given and how the electronegativity affects in the delta values you can see in this particular amines. Okay, so here the this carbon is showing the 35.9. This uh, attached with the electronegative, more electronegative nitrogen, and where this carbon is, it is okay some way this nitrogen. It is not directly attached with this one, so you can see the 17, and it is double to this one, right? So this is only due to the attachment of and the non-attachment of the carbon with the electronegative atoms. And in example, you can see, right? So here this particular carbon in same, it is chloroethane. So in the chloroethane, okay, in the chloroethane, you can see this carbon is showing the 39.9 delta value, and this is 18.7. This difference is due to this carbon is directly attached with this more electronegative chlorine here, and it is not directly attached with this chlorine. Okay, same criteria. And this carbon is attached to fluorine here. So we have the 79. So from left to right, okay, from left to right, so where the increase in the delta values is taking place here. Okay, in the same alkene derivatives, where electronegative atom is there, here the chlorine is there, here is oxygen, right? If, when you observe these two carbons here, two carbons are also same. So same length of molecule here, same number of carbons in 4 cases. but difference in here activities nature and the hybridization. Yeah. So here generally the hybridization, we know that, right? P to SP. So when you see these three hybrid, so electronegativity is SP, SP3, right? So is hybridization, right? So you see here this hybridized carbon is uh, 65 to 110 and S2, right? If it carbon 116 to and it's 5 to 100 here, right? Okay, as statement is of the electron of various dimensions. But here we are observing this sp2, okay, the sp, okay. So some what is it disorder, okay, you can see the disorder in this where the sp2, okay, it come for front then this one. So this disorder is due to the anisotropic effect. Okay, nice. Anisotropic effect of the varieties of alkene. So this carbon, okay, this carbon falls in this diap. Okay, so the magnetic region and olefin carbon. Okay, sorry, not olefin. It is olefin carbon falls in the diamagnetic region, and alkene carbon. Okay, so they falls in the paramagnetic here. So due to this, okay, so where this is the secondary magnetic field, right? So these two carbons won't experience the diamagnetic field. Okay. So due to this we call this phenomena is anisotropic effect, and due to this reason where the sp2 is having higher delta values 140. Yeah, next isomeric effect. Yes. So here is a where this compound that unsaturated here, right? So where it is involving in regions delocalization. So due to delocalization, yes, where the particular carbon is means the directly attached to the uh, Yes. So in the alpha beta unsaturated carbon compounds, so generally here you can see alpha, this is alpha, this is beta here. Okay. Uh, carbon is in the D localized. Is not falling in the. So where carbon will falls in the falls in the shield region, not delocalization, it falls in the right? So it won't involve in the delocalization like this alpha, this is beta, right? So it is uh, falls in this particular de-shielded region or the downfield here. Yes, the conjugation. So here conjugation decreases the data values. Okay, having the conjugation, so it decreases the delta values here. Here, in this example, you can see it is conjugated. It's unconjugated. Right? This is conjugated. This due to unconjugation, we have pairs at 140.2 value, and here is a is involving in the conjugation where the decrease right, so delta value 137, it becomes 137, right? Due to the unconjugation, the conjugation is proportional to conjugation is inversely proportional to the delta here. Heavy atoms, so heavier isotope atom called multiple, okay, multiple heavier atoms, okay, large atoms. So where the large atoms decrease values, but the heavy atoms decreases means it is proportional again. And here you see in this example, see fluorum, where it is 10 here. Here is a dimethyl, dibromomethane, it is 21, and tribromethane, it is 12 here, and tetrabromo, right? So very less. So you see increase of the heavier atoms. Okay, with the increase of the number of heavy atoms, delta values means tremendous decrease in the delta value. It is minus here. Why? Because you see there is a steric repulsion. Okay, there is a steric repulsion between the heavier atoms here. Okay, and here is a in right. So here is also we have the three bromine here. Okay, so between these means value is decreasing. Here is so it's sorry. Yeah. So, right. So it is a separation. This much separation. So these are far away. So we have the increased values. There is only one alkyl, one heavy atom. So 10. So increase in the number of heavy atoms, the delta values will be decreased. Next, hydrogen bonding, very, very important factors which affecting the delta value here. Yes, so here is hydrogen bonding. In the hydrogen bonding, we have the intermolecular hydrogen bonding and intermolecular hydrogen bonding. So here the presence of hydrogen bonding increases the delta values. Okay, so presence of hydrogen bonding, delta values will be increases here. So in this benzaldehyde, you can see there is no hydrogen bonding here. So there is no hydrogen bonding in the benzaldehyde. So we have the 191.5. And here is a what is this hydroxy benzaldehyde, ortho hydroxy benzaldehyde here. So with we have the intramolecular hydrogen bond. Okay, intramolecular hydrogen bonding here. So we have the 196 value. So here is 191, here is a 196, right? So with the hydrogen bonding increases the delta value. And isotopes. So presence of isotopes increases. Okay, so presence of isotopes where it decreases the delta values. Okay, isotopes decreases the delta value. So here is isotope here, right? Deuterium isotope. Here is a 53.1. Here is a 53.8. Right. So presence of isotope, the delta value. Okay, isotope is inversely proportional to this delta values here. And the solvent effect. This is one of the important factor. Right. So with in the solvent generally we have the polar solvents and non-polar solvents here. So polar solvents, right? Polar solvents increases the polarity. Okay, so polarity directly proportional to the delta. With increase of polarity, delta value also increases. Right, the polarity increases the delta value here. And electronegativity. Electron deficiency. Yes. Right. So here having that electron deficiency, where the delta values, electron deficiency decreases the delta values here. Okay, electron deficiency decreases the delta values. So here you see where it is okay, so secondary carbocation here. This is secondary carbocation. This is tertiary carbocation. Right. So two methyl groups are there. Right. So in this we have two plus I groups. Plus I groups here. It is in the tertiary we have three plus I groups. Right. We have three plus I groups. So the delta values, right? Delta values will be increases. Okay. Delta values will be increases. Right? So is affecting the values of the C30 spectrum. And coupling in the C30 spectra. So we'll see in the next class. So I am stopping here.